All right, everybody, we're back. We only have a short segment here with loose ends in nuclear magnetic resonance. We need to talk about what solvents are appropriate to use in nuclear magnetic resonance experiments. We can't choose a solvent that has hydrogens in it because, as you know, solvents are the vast majority of a solution. And if you had a solvent that had hydrogens in it, you would see one peak in your NMR or two peaks if your solvent had two types of H's, etc. So we have to pick solvents that are not active in the proton NMR region of the experiment, which runs from 0 to 12 ppms if you look at your chart. So we have some popular NMR solvents over here. So we have to have nonpolar and polar solvents because we have nonpolar and polar organic molecules that need to be dissolved. Carbon tetrachloride is very nice as a nonpolar solvent, but it's very nasty as a chemical. We have to treat it with ultra caution. It is a known carcinogen, so we want to avoid it if we can. Deuterochloroform is easily made from chloroform using acid-base chemistry and hydrogen exchange with deuterium. It is the most popular solvent. It's nonpolar and it's easily made, so it's not too expensive. Making deuteromethanol is a lot more expensive, so deuteromethanol, it gives you a polar solvent called per-deuteromethanol. All of the H is replaced by deuterium, and that would be used for polar molecules. Very polar molecules, you need a water equivalent. Heavy water is deuterium oxide here, and those are popular solvents. In the old days, when our machines didn't have computers attached to them that could tell us where 0 ppms were based on solvents like we use now, we used 1 drop of this standard. We dropped it into our solution, and because silicon is less electronegative than carbon, that puts the electrons closer to these H's. We call that shielding, if you remember from our previous lecture, and it shields to 0 ppm. That's where we would set the 0 in the machine based on this NMR standard. We don't use that anymore. We have computers that'll lock into the trace amount of normal chloroform found in every sample of deuterochloroform, and it'll say, oh, that peak's supposed to be at 7.2, therefore this over here should be 0, and it sets it for you there. You just have to tell it what solvent you're using. Anyway, I'm never going to ask a question about how computers set the 0 nowadays versus in the old days. I will ask you questions like, which of these is an appropriate solvent for a nonpolar NMR experiment? And I might have a few choices, these being 2 of them. You'd pick those. And any solvent with hydrogens in it, you'd say no. So if I gave you normal chloroform where there's an H here, you would not pick that as a good NMR solvent at all. Okay, so solvents are done. C13 NMR. There's a lot more to NMR than I will be dealing with in this course. We're pretty much done with everything I need you to know. C13 experiments can be very useful. I'm only going to point out one of their uses right here. And here's the deal. C13 is the only nucleus of carbon that's active in an NMR experiment that's available in significant amounts in carbon, because if you look on the periodic table, you got this mass of carbon at 12.01, you know not 100% of carbon is C12, which has a mass of exactly 12.00. Some of it has a higher mass, and this is it. 1% of all carbon on this planet anyway is C13 carbon with the extra neutron in its nucleus to give it a mass of 13. And only 1% means it is almost impossible for neighboring carbons, that's 2 adjacent carbons, to both be C13. Just doing a simple statistical analysis, you get 1% of 1%. That are the odds of 2 consecutive carbons being C13. Why am I saying all this? Well, there's no communication between carbons in the C13 experiment because they would have to both be C13s adjacent to each other. But you also need to remember that each hydrogen on a carbon is an electromagnet itself, and that will influence the carbon's peak. So if we start with B here, why would this be a doublet, the C13 peak? It has nothing to do with neighbors. Neighbors are irrelevant in C13 experiments. Neighbors don't talk to each other because they don't exist. 1% of 1%, close to 0. But there's one H on B, and it's either rotating clockwise with or against the applied magnetic field, or it's going counterclockwise against or with, and they have an influence of moving it downfield if it's lined up with a magnetic field, or upfield if it's aligned against the magnetic field. Am I going to test you on any of that? No. I'm going to give you the one question that's worth 1 point very soon. I'll just talk about this peak at 20, D is at 20, don't even worry about why. Why is it a quartet? Well, there's 3 H's living at home on that C. Each one of them's a magnet. 3 plus 1 is 4, quartet. Anyway, the test question, I'm going to cut to the chase. How many signals will appear in the proton decoupled C13 NMR spectrum? That is just code speak for how many types of carbon are in this molecule. What happens in the proton decoupling reaction, it's not a reaction, proton decoupling experiment, is that we make every one of these peaks into a singlet by washing these carbons in a radio range of frequencies that makes all of the hydrogens start their spins resonating up and down so fast the carbons can't tell if they're up or down. So we have it's like white noise in the proton NMR energy region, and it makes everything into a singlet because the carbon can't tell if the H's are different anymore. And it's much easier to count singlets, isn't it? If you had these peaks getting close to each other, it would be hard to tell where a triplet started and where a quartet left off with overlap, but it's much easier to count singlets. So the question is, one question could be, I'll give you a picture here and ask you how many signals would be in the C13 spectrum that's proton decoupled for that molecule, and your answer would be 4, because that's one type of carbon. It's different than the D because it's on a CH2 over here and it's on a CH over here. They're different. This is unique and this is unique. 4 unique types of carbon. So watch out for things like symmetry. I'll find an example with symmetry and be right back. I have to do this and then stop. And I think you can still hear me. Looking at the real test here. Get a real question, and we'll just answer the last test, fall 19. I know you can't see what I'm doing. There we go. Well, that's quite a molecule. Snip it and bring it over and start the video again. I have to talk to myself or I'll forget to do these things and it'll be a disaster. And we'll sneak it on the bottom of this page. All right. I started the video again. We're zooming over to here. And we got this molecule from fall 19. Test 1. I always have a little symmetry in these molecules. So we're looking for unique carbons. Let's just put a highlighter on them. That carbon is unique in this molecule. I think everything on the right side is unique almost. unique, 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 unique. Oh, changed my mind. That's unique. That's the same. Those are both CH2s attached to CH2s attached to OCH3s. The whole group's identical, so the individual carbons in there are also the same. And these C's. So we'll put highlighter dots on each one and count our highlighters. This one, this one, this one. This benzene looks symmetrical too. There's CH2 here, CH2, CH2, CH2. Nope, don't use the highlighter. And we've got these two identical. And we got these two identical. And highlighter. And unique, unique. Same, same. And unless I missed a carbon, which I know you'll let me know if I did, we just count our dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. And I'll pause here and we'll go to the practice test to see if I missed any. And stopping video. Got the answer key open somewhere. Uh-huh. There we go. Trying to bring it over here. All right, so video's back on. And we're sharing. We're on our NMR sheets here, going down. There they are. And it looks like we have 19, so we got the answer key there too. I think we got it right. Okay, that's worth a point. 19 carbons. So that brings to a close this segment here. In my mind, it just came to me, there was a small mistake in our previous example. I didn't include the oxygen. So I will have that fixed on the starboard that I post. I'll put the oxygen where it belongs. It was right after the benzene and before the carbonyl. That was the only place we could put it. And I will see you on the other side, 5 minutes. And adios.